Welcome students to the computer science class. In this tutorial, we will learn about the hexadecimal number system. In the previous tutorial, we have seen the decimal number system, the binary number system, and the octal number system. We have also seen the conversion, the way to convert a binary number to a decimal number, an octal number to a decimal number, and an octal number to a binary number. So we will see all of them again in the conversion part after we do with the hexadecimal number system. We will see the hexadecimal number system now. So what is an hexadecimal number system? It is a number system that uses 16 digits, that is 0 to 9 and A to F. Remember, capital A to capital F, not small a to small f. It is in capital. The hexadecimal number system uses 16 digits including 6 letters of alphabet. Hex means 6. These include the symbols 0 to 9 and A to F. The primary reason why hexadecimal number system is used with computers are it can represent the binary values in a more compact and readable form. So you have seen and you will also see now, and the conversion between the binary and hexadecimal number system is very efficient because it can be represented in a more compact and readable form, and the conversion between binary and hexadecimal number system is very efficient and easy, right? So there are two reasons why hexadecimal number system is used with the computers. Okay, so we will see how it is very easy. You have already seen for octal to binary, right? Binary to octal. Now you will see for hexadecimal. An 8-digit binary number, a byte, can be represented by 2-digit hexadecimal number. For example, the decimal number 79 or 79, whose binary representation is 01001111, can be written as 4f in hexadecimal. How it is 4f? You have to make a group of 4. See, group of 4, here it is 1111, and group of 4, this one is 0100, right? So 0100 means what? It is 4, and 1111 it is f. So you will see how to convert 79, the decimal 79, to a binary. How you got this? Okay, now you learn about how to convert this representation to a hexadecimal representation. That is how 01001111 is equal to 4f. Okay, how 01001111 is equal to 4f. 1 ff, that is 1 into 16 to the power 2 You want to convert this into a decimal number. So how you can convert? 1. Similarly, you will convert as you have converted for an octal number. So each of the positions is of the powers of 16. This is 16 to the power 0, 16 to the power 1, 16 to the power 2. So 1 into 16 to the power 1, f into 16 to the power 1 into this one into 16 to the power 2, f into 16 to the power 1, and f into 16 to the power 0. Anything to the power 0 is a 1, f into 1, 15 into 1, f into 16 to the power 1, f into 16, that is 15 into 16, and 16 to the power 2, that is 256 into 1. So the number is 511. Right. The decimal equivalent of hexadecimal number 1FF to the base 16 is 511 to the base 10. I have got. Since there are only 16 digits in the hexadecimal number system, 4 bits are sufficient to represent any hexadecimal number in binary. So 4 bits are sufficient to represent any hexadecimal number in binary. So in binary, the numbers are represented. You see there are 4 bits. I have already told you for the maximum value you have to consider the number of bits. The number of bits you need to represent the maximum value. For an octal number you have seen for 7, that is the maximum value of octal representation, octal number system is 7, and you can represent 7 with 3 bits. But for 8, 9 and onwards up to F, you need 4 bits. You can represent the maximum digit of an hexadecimal number, that is F, with 4 bits. See, after 15 you cannot represent anything with F. Right. So F is the maximum hexadecimal number, and it can be a hexadecimal representation, and it can be represented by 4 bits. So you have to take 4 bits for each of the representation. Maybe we don't require up to 7, but for 8 you need. So for you have to keep the provision for all the digits. You cannot just represent the smaller by only 3 bits and the bigger by 4 bits. That is not allowed. So for representing all the items, whatever the number of bits is required, you have to take that. You have to keep provision for that. Okay. So for representing up to F, you need 4 bits, and you can represent any hexadecimal number with 4 bits. Okay. The hexadecimal number, see from the table, if you are supposed to memorize this table up to F, the binary representations of 0 to 15, you can see 0 to F, 0 to F, 0 to 9 and A to F. You have to memorize the corresponding binary representation. So the hexadecimal number 4B3A translates to the following binary number. 4 is 0100, B is 1011, 1011, right? 3 is 0011, A is 1010. A is 1010. So it is 0100101100111010. You cannot segregate it, but you have to tell it all at a time and write it all at a time. Right. So let's take another example, 3CAB. If someone tells you to convert the hexadecimal number 3CAB, so how will you convert? 3 means 0011, right? 0011. C is 1100. C is 1100. A is 1010. B is 101. Like that. So you can convert a hexadecimal number very easily to a binary number. Okay, so that is why it is used in computer arithmetic. Now some conversion to and from other number system. First we will see decimal to binary number system. We have already seen how to convert binary to decimal, right? We have seen for 9, we have seen for 11, 12, 13. We will now see how to convert a decimal number to binary number. So what is the first step? Divide the decimal number by the value of the new base. So what is the new base? It is 2. So you will divide the decimal number by 2. Record the remainder from step 1 as the rightmost digit, least significant digit of the new base. Divide the quotient of the previous division by new base. Record the remainder from step 3 as the next digit to the left of the new base. Repeat step 3 and 4, recording remainders from right to left until the quotient becomes 0 in step 3. Until the quotient becomes 0. See, the quotient is 0. Where is the quotient written? Quotient is written over here and remainder is written over here. So let's see, 42 is the decimal number which has to be converted to a binary. So divide it with the base of binary, that is 2. The quotient is 21. Remainder is 0. Again divide 21 by 2. Quotient is 10. Remainder is 1. Again divide 10 by 2. Quotient is 5. Remainder is 0. Again divide 5 by 2. Quotient is 2. Remainder is 1. Again divide. Quotient is 1. Remainder is 0. Divide again. You will get a 0 and remainder 1 over here. Now you have got all the remainders after division. Write the remainders from bottom to up. Right? Record the remainder the next digit to the left of the new base number. Recording the remainders from right to the left until the quotient. So right to the left means you have to record the remainder right to the left. Either you write it like this one, 0. First you write this 0 to the rightmost, then you write 1 over here, then you write 0, then you write 1, then 0, 1. So what I follow is I do it in the reverse order. The order of remainder, the order in which I got it, not I got it, in the reverse order in which I got it. So 1 I have got last, so I will write 1, then 0, then 1, then 0, 1, 0, right? So write the remainders in the reverse order you have got. So bottom to up direction. Okay. Then you get the corresponding binary number. Next is binary to decimal conversion. Binary to decimal conversion you have already done. You have done with a small number. I have already done with a small number like this, right? For 10, 1, 0, 1, 0. Now we will do with a bigger number 1, 0, 0, 1, 0, 1, 0. Okay. So let's see. You have already learned. You have to mark the positions. So this is 2 to the power 0, this is 2 to the power 1, 2 to the power 2, to the power 3, to the 4, 5 to the power 6, right? Like this, 0, 1, 2, 3, 4, 5, 6. There are up to 6. So 2 to the power 6 into 1. See, where are the ones? Ones are in the places 2 to the power 6, 2 to the power 3, 2 to the power 1. Right? See, 2 to the power 1, 2 to the power 3, 2 to the power 6. What is 2 to the power 6? It is 64. What is 2 to the power 3? It is 8. What is 2 to the power 1? It is 2. So 8 plus 2, 10. 10 plus 64, it is 74. Got? The decimal value is 74. So don't calculate the zeros, because 0 into 2 to the power anything, whatever is the 2 to the power, the value will be 0. You multiply something with 0, you will get a 0, right? So only calculate the positions for 1. Okay. So don't calculate 2 to the power 5. It is 32, it is 16, this one is 4, this one is 1. So you have 0 into those. That is 0 into 32, 0 into 16, 0 into 4, and 0 into 1. So these are zeros. And you have 64 into 1, 8 into 1, and 2 into 1, giving you 64. Okay, so this binary number is equal to 74 in decimal. Clear? Next is decimal to octal. Decimal, that is base 10 to base 8. The conversion of decimal to octal is similar to the conversion of decimal to binary. The only difference is in the base. In this number system, we have to divide the decimal number by 8. So what were we doing in case of our decimal to binary? We were dividing by 2, dividing by the base of the binary number system. Now we'll divide the decimal with the base of the octal number system, right? Divide it with the base of octal number system, and similarly collect the remainders and write the remainders in the reverse order. We will go on dividing till we get a 0, till there is no remainder. See, we have taken 5 over here and nothing is left. So 5, 0, 1, 0 written in the reverse order that we have got the remainder will give you the corresponding octal number. So 2586 is equal to 5010. So you will divide, get the quotient over here, Write the remainder over here. Again divide, get the quotient, get the remainder, again divide. Now here I think they have made a mistake. Actually this came downward, right? No mistake is there. Uh, when you are doing this, 5 8 is a 40. 5 8 is a 40, and actually this will be over here. Okay, you don't get any remainder right over here. After dividing 2568 by 8, you get a quotient 321 and you get a remainder 0. So this remainder will be over here. Okay, this remainder over here, then 1 will be over here. 1 will be over here. So it is given wrongly one step up, right? So there will be some correction over here. The remainders are given rightly, but it will be one step downward. This is printed wrongly. It will be like this. The remainders will be after you divide 2568 by 8, the quotient is 321 and the remainder is 0. Okay, so we will make the correction with the red ink, and it should fit in this. It should fit. Right. Let's see. This 0. This 0 comes over here. Right. After dividing 8, after dividing 2568 by 8, you get the quotient 321 and remainder is 0. Again, after dividing 321 by 8, you get a quotient 40 and the remainder is 1. Remainder here is 1. You divide 40 by 8, you get quotient 5. The remainder is 0, right? 5 8 is 40, there is no remainder, 0. Again, you divide 8, you divide 5 by 8, you get a 0 over here, and 5 is brought over here, right? So this will be your correct form of remainder. So 5 0 1 0. So 5 0 1 0. You write it from in the reverse order, 5 0 1 0. It is all right, but it has gone one step higher. There is no remainder. Okay, here is no remainder. So you cut this. I cannot cut it over here. Here there will be no remainder. This 0 is over here. This 1 is over here. This 0 is over here. This 5 is over here. Right? And left 0 has got no meaning. Okay. There will be no 0 in the left. So 5 0 1 0 is the corresponding octal number to this 2568 in decimal. Okay, so what you have to do? You have to divide the number in decimal with 8. Divide by 8 like you have divided by 2 while getting a binary from a decimal number. So now you want to get a octal. You want to get octal from decimal. So divide the decimal by 8. So divide with the base of the number system you want to get. You want to convert to. Right? I hope I am clear, and any questions you ask me so that I can clear your doubts in the next video. Okay. Decimal to hexadecimal. This one I have done for decimal to octal. Now we will do decimal to hexadecimal. So base of hexadecimal is 16. So the base with which we have to divide the decimal is 16. We want to convert it to the hexadecimal, so we will divide it by 16. Divide it by 16 and get the remainder. What is the remainder? Write it from in the down to up direction in the reverse order. Here I think is the same kind of printing error is there. After you divide 1000 by 16, you get a quotient 62. The remainder is 8. Right. So you do the division, you know how to divide, and you know how to collect the remainder. These are the remainders. So write the remainders. You will be getting remainder of this, then this, then this. So you will write the remainders in the reverse order from down to up direction to get the corresponding hexadecimal number. So 1000 in decimal is 3E8 in hexadecimal. Now this E has got a significance. E means it is 14. The remainder must have been 14. So that's why they have written it E. As you are using the hexadecimal number, 14 is written as E. So you cannot write 14 over here. You have to write it E. So 8E3. Write it in the reverse way, 3E8 is the corresponding hexadecimal number. Okay. Next you see bit, byte and nibble. We have already discussed about bytes, bits, bytes and nibble. Let's see what is there. The smallest unit in computer processing is a bit. Bit by bit it is processed. It is a unit of data that can be either of two conditions, 0 or 1. Groups of bits make up storage units in the computer called characters, bytes or words, which are manipulated as a group. Each of zeros, each of the zeros and ones in the following diagram indicates a bit. This is a bit. So there are 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. 8 bits in this representation called a byte. Group of 8 bits is called a byte. A group of 8 bits called a byte. Evidently, many such groups can be made in the binary system. So with this group, you can see there are 8 bits. So for each of them, you can have many representations, right? For this place you can have two representation. For each of these two places there can be 2 into 2 representations. For each of this, like this. So it will be how many? 2 to the power 8. See, here it is written. Exactly speaking, 2 to the power 8 or 256 bytes are possible, and they can represent 256 characters. Clearly, these 256 are enough to represent 26 letters of the alphabet, both in capital and small, numbers from 0 to 9, punctuation marks, currency symbols, and some special symbols. These 256 bytes are represented by different binary numerals starting from 0, 0, 0, 0, 0, 0, 0, 0, and ending with 1, 1, 1, 1, 1, 1, 1, 1. So, how is this 256? It is 2 to the power 8. You can well imagine, you can write for each place either 0 or a 1. So for each of these two, you will get 2 into this. For each of these two, you will get 2 into this. So for each of these 8 places, you will multiply 2 8 times, right? For this place, you will multiply 2. For this, you will multiply 2. For this, you will multiply 2. So in this way, you will multiply 2 8 times, making it 2 to the power 8, making it 256. So 256 different such patterns can be made with a byte, which are sufficient to represent all the letters, both in capital and small, the special symbols, the currency, punctuation marks, etc. Okay, so that is about a byte. A nibble is a half of a byte. A nibble is a collection of bits on a 4-bit boundary. That is, 4 bits is called a nibble. 8 bits is called a byte. If the last digit of a binary number is 1, the number is odd. If it is 0, the number is even. That is 1101 represents odd number 13. 10010 represents an even number 18. In a base n representation of a binary of a number, no digit exceeds n minus 1. Every digit of the base 2 number must be 0 or 1. It cannot write other than 0 or 1 in a binary number or a base 2 representation, right? So that these things you have read already. So I think there is no confusion. If you get any confusion relating to the conversion, if you have any confusion, just comment your doubts. I will try to clear them in my next tutorials. Okay, read the chapter well. I hope there will be no doubts. Thank you all.